Today we'll continue number theoretic function, and this is one important topic in number theory. This topic is important also B.Sc School Service Commission examination, JAM and Public Service examination, and as well as RMO NMO Olympiads. So now start some important number theoretic function. One of them is Euler phi function and tau functions. So now we'll define the Euler phi function first. So our first recall is basically about Euler phi function, or you can say Euler phi function. So what is the definition of Euler phi function? The Euler phi function, the Euler phi function or phi function is denoted by phi and is defined by phi of 1 equals to 1 and phi of n equals to the number of positive integers less than n and prime to n, less than n and prime to n, and here n is basically greater than equals to 2 and n belongs to natural number. Okay, so this is basically definition of Euler phi function or Euler phi function. So here important note, so what will be the phi one? This is basically 1, and second note, phi of n, that will be number of positive integers less than n, and the number of positive integers less than n and prime to n, less than n and prime to n, and where for all this is n greater than equals to 2. Okay, so here as for example, if we calculate phi 4, so what will be the value here? You will see the number of positive integers less than n and prime to n. Okay, so less than n, less than 4, that means 1, 2, 3, this integer is less than 4. And just you check GCD of 1 and 4, this is 1. GCD of 2 and 4, this is 2, and this is not equals to 1. That means 2 is not prime to 4. And GCD of 3 and 4, this is also 1. So there are only two integers which are basically less than 4 and prime to 4. So phi 4 equals to 2. Okay. Similarly, here you can check phi of 20, that will be 8. So in that way you can calculate the number of positive integers less than prime to n. Okay, so that we can write in that way, that is equals to all those m such that 1 less than m less than n, and GCD of mn equals to 1. That cardinality is considered as the phi n for all n greater than equals to 2. Now we come to next important recall. So this is basically definition of Euler phi function. Here the question, maybe you have asked the question, define Euler's phi function, and this question you may be asked for 1 mark question, and this question important for the graduation examination. Now there is another important recall. Recall is about say let P be a prime number. P be a prime number. Then you can easily check that. So what will be the phi p? So phi p will be the p minus 1. Why? Because since every positive integer less than p where p is prime is always prime to p is always prime to p. Okay. So here say you are trying to calculate the phi p where p is prime. You just check 1, 2, 3, 4, p minus 2, p minus 1. All are basically less than p, and you also check GCD of m comma p, that will be 1 for all m less than p. That you can check. So that means all the integers less than p and less than p, they are basically prime to p. So phi p will be p minus 1. Okay. As our observation here, GCD of m comma p equals to 1 for all m belongs to natural number and m less than p. Okay. So here the possibility of m, it may be 1, it may be 2, it may be 3, it may be 4, and the last possibility is p minus 1. You just count the number of elements, obviously it will be p minus 1. Now our next important recall 3, the Euler phi function is a number theoretic function. And recall 4, it is also multiplicative function. So Euler phi function is also multiplicative function. You can prove it. Why it is multiplicative? Since GCD phi of mn equals to phi m into phi n. If GCD of mn equals to 1. Now we come to one important question. So you have to find out the number of positive integers. So the question is question 2, and that question is asked in Calcutta University B.Sc Mathematics Honours Examination. The question is find the number of integers. Find the number of integers less than n and prime to n, less than 324 and prime to 324. So how to solve this kind of problem? Before solving this problem, you must recall some basic facts. What is the fact? This is the theorem of this topic. The theorem is if n equals to p1 to the power alpha 1, p2 to the power alpha 2 some pk to the power alpha k. This is basically canonical representation of the positive integer n by fundamental theorem of arithmetic, where all pi's are distinct primes. Then phi of n, that will be, and all alpha i's are basically natural number for all I. then phi n equals to n into 1 minus 1 by p1, 1 minus 1 by p2, 1 minus 1 by p3, 1 minus 1 by pk. By using this result, we can solve this problem. So first, you will do the prime factorization of the number 324. So here our n equals to 324. And the canonical representation of 324, this is basically 2 square into 3 to the power 4. So by using this fact, therefore the phi of 324, that means the number of integers less than n, less than 324 and prime to 324. So that will be phi of 2 square into 3 to the power 4. That we can use by this formula. So by star, what we can write 2 square into 3 to the power 4, 1 minus half, 1 minus 1/3. And just you simplified it and you will see this value will be 108. You have asked another important question. That question is also important for Calcutta University and other university examination. If n is, find the number of integers, find the number of positive integers, that will be number of positive integers less than n, less than 900 and prime to 900, prime to 900. So now how to solve? Again, what is given here? Here n equals to 900, and that 900 we can do the canonical representation by using fundamental theorem of arithmetic. The 900 we can write, this is 2 square into 3 square into 5 square. So therefore by the above fact, the phi n, that means phi of 900, that will be 2 square into 3 square into 5 square. So that will be into 1 minus half, 1 minus 1/3, 1 minus 1 by 5. And you just do the simple calculation and you will see this value is 240. So thus our answer is, thus the number of positive integers less than 900 and prime to 900, this is equals to 240. Here you can have this kind of MCQ type question. Okay, the number of positive integers less than 900 and prime to 900 is, there is option A 200, option B 899, option C 240, and option D 108. So 240 is the answer that we have done in the previous problem. Now we have to prove these two important theorems. So what are the theorem? So here theorem 1, that is probably a problem. If P be a prime, and K is a positive integer and K belongs to natural number or positive integer, then prove that then phi of p to the power k, that means number of integers less than p to the power k and prime to p to the power k, that will be p to the power k into 1 minus 1 by p. Or you can ask the question in that form. So this is question 4. And that question is also asked in Calcutta University examination. Let p be a prime, and k is a positive integer. Then prove that phi of p to the power k, that will be p to the power k into 1 minus 1 by p, where phi is basically represent the Euler phi function. So now, how to solve this kind of problem or how to prove the theorem? So what is exactly given? So here given, first is p is prime, and second is k is a positive integer. What we have to prove that? We have to prove that phi of p to the power k, that means number of positive integers less than p to the power k and prime to p to the power k, that number will be p to the power k by 1 minus k. That we have to prove. Now, we need to think about the number of positive integers less than p to the power k and prime to p to the power k. So, the positive integers, this is less than equal p to the power k, and which are not prime to p to the power k. Prime to p to the power k are, that positive integers are, so I said not prime to p to the power k. So p will be one number, 2p is also 3p, p to the power k minus 1 into p. So these numbers are basically less than equals to p to the power k, and it is not prime to p to the power k. So therefore the number of positive integers less than p to the power k and prime to p to the power k, that number will be equal to, so total number is p to the power k, and hence you need to count how many numbers are there which is not prime to p to the power k. Okay, that you need to count. So how many numbers of this type? This is basically start 1 into p, 2 into p, 3 up to p to the power k minus 1. So the remaining numbers will be, this number is not prime to p to the power k, so the remaining numbers, total numbers p to the power k minus p to the power k, that number will be prime to p to the power k and less than p to the power k. So this is basically the number of positive integers less than p to the power k and prime to p to the power k. So this is the definition of phi p to the power k. So that will be pick common, take common p to the power k, that will be 1 by 1 minus 1 by p. So what we proved here, so therefore we proved here phi p to the power k, this is p to the power k into 1 minus 1 by p. So we have proved the result. Next important theorem, this is theorem number 2, the Euler phi function. So what is the theorem? If n equals to p1 to the power alpha 1, p2 to the power alpha 2, pk to the power alpha k, this is the canonical representation where p1, p2 dot pk are prime to each other, are distinct primes, okay, or prime to each other, or prime to one another, then the phi n, that will be n into 1 minus 1 by p1, 1 minus 1 by p2, 1 minus 1 by pk. The result we have shown here. This is the result, and by using this fact we have already proved how to calculate the Euler phi function of a big number. So now we'll prove, but maybe asked the theorem in the form of question. Let n greater than equals to 2 and n equals to p1 to the power alpha 1, p2 to the power alpha 2, pk to the power alpha k, where all pi's are distinct primes, and all alphas are positive integer, then prove that phi of n or phi of n, that is n into 1 minus 1 by p1, 1 minus 1 by p2, 1 minus 1 by pk. So that question is asked in Calcutta University honors examination. Another thing is how to prove this kind of problem. So now we'll come to the solution or the proof of this theorem. So what is exactly given? It is given here n is greater than equals to 2 and n equals to p1 to the power alpha 1, p2 to the power alpha 2, pk to the power alpha k, where in the canonical representation it is mentioned pi's are distinct primes. That means GCD of, if we take any pi pj, that will be an for all I and j, and all pi's p1, p2, pk are primes. And it is also given all alpha 1, alpha 2 dot dot alpha k, they are basically positive integers. What we have to prove? We have to prove that phi of n, that will be n 1 minus 1 by p1, 1 minus 1 by p2, 1 minus 1 by pk. That we have to prove. Okay, so how to prove this kind of fact? So what we know by the previous theorem, if p is prime, then phi p to the power k equals to p to the power k into 1 minus 1 by p. So since p1, p2 dot 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 pk are all primes and alpha 1, alpha 2 dot dot alpha k, they are positive integers. So what we can write? Phi of p1 to the power alpha 1, that will be p1 to the power alpha 1 into 1 minus 1 by p1. Phi of p2 to the power alpha 2, that will be p2 to the power alpha 2 1 by 1 minus p2. Dot phi of pk to the power alpha k, that will be pk to the power alpha k 1 minus 1 by pk. So now since GCD of p1, p2, this is basically 1, so that implies GCD of p1 to the power alpha 1, p2 to the power alpha 2, this will be 1. So what we can write? So phi of p1 to the power alpha 1 into p2 to the power alpha 2, that will be phi of p1 to the power alpha 1, phi of p2 to the power alpha 2, because since phi is a multiplicative function and GCD of these two number is 1. So that means it will be phi p1 to the power alpha 1 into 1 minus 1 by p1, and P2 to the power alpha 2 into 1 minus 1 by P2. So that will be P1 to the power alpha 1, P2 to the power alpha 2, 1 minus 1 by P1 into 1 minus 1 by P2. Similarly, so this is basically what we get. Phi of P1 to the power alpha 1, P2 to the power alpha 2. So this is basically star. Again, since GCD of P1 to the power alpha 1, P2 to the power alpha 2, P3 to the power alpha 3, that GCD is 1. You will check, because as P1, P2, P3 are distinct primes, and alpha 1, alpha 2, alpha 3 all are natural number. So again phi is multiplicative function. So pi of P1 to the power alpha 1, P2 to the power alpha 2, P3 to the power alpha 3. That we can write phi P1 to the power alpha 1, P2 to the power alpha 2 into phi P3 to the power alpha 3. Just take 2. So now by star, that is basically P1 to the power alpha 1 into P2 to the power alpha 2, 1 minus 1 by P1, 1 minus 1 by P2. This is basically by star. Here you will see we have already proved this result. And phi of P3 to the power alpha 3, that will be P3 to the power alpha 3 into 1 minus 1 by P3. So what we get? P1 to the power alpha 1, P2 to the power alpha 2, P3 to the power alpha 3, 1 minus 1 by P1, 1 minus 1 by P2, 1 minus 1 by P3. If we continue this process up to k times, so obviously we will get the result. That way, so what we are proceeding with similar arguments, we have phi of P1 to the power alpha 1, P2 to the power alpha 2, P3 to the power alpha 3, Pk to the power alpha k. So that will be P1 to the power alpha 1, P2 to the power alpha 2, Pk to the power alpha k into 1 minus 1 by P1, 1 minus 1 by P2, 1 minus 1 by Pk. And that is basically n. So that means phi of n equals to, this value is n. So n into 1 minus 1 by P1, 1 minus 1 by P2, 1 minus 1 by K. So we have proved the theorem or problems. Okay, so now we come to some important problem. So question 4 is done. Now we come to the question 5. So this is you can consider question 4. This is question 5. Now question 6. Okay, this is also important for Calcutta University honors examination and also any other university. If n be an odd positive integers, if n be an odd positive integers, then prove that phi of 2n, that will be 2 into phi n. Okay, sorry, that will be phi n. While n is odd positive integers. Okay, so how to solve, how to prove? What is exactly given? It is given n is an odd positive integers. What we have to prove? Here we have to prove that phi of 2n, this is basically phi of n. These are basically safe. So start phi of 2n. So before that, since n is odd, so what we can say? Phi of, we can say GCD of 2 and n, this will be 1. Because n is odd, that means there is no factor as 2. So GCD of 2 and n, that will be always 1. And since phi is multiplicative function, so therefore phi of 2n, that will be phi 2 to phi n. Because since we know phi of mn equals to phi m into phi n, if GCD of mn, this is equals to 1. So yeah, GCD of 2n equals to 1, so we can write this. So phi of 2, that means number of integers less than 2n prime 2, so this is equals to 1 into phi n. Why? Because since phi of 2, that means number of integers less than 2n prime 2, so 2 is prime, so phi of 2 will be 2 minus 1, this is basically 1, as 2 is prime. Okay, and we know the result, we know the recall is phi of any prime p, that will be p minus 1 if p is prime. So this is basically phi n. So what we have proved? So thus we proved that here phi of 2n, this is exactly equals to phi n if n is odd. Now if n is even positive integers, so what will be the result? Phi of 2n equals to 2 into phi. So the next question, question number 7, this is also important for Calcutta University examination. So if n is an even positive integer, very important. If n is even positive integer, then prove that phi of 2n, this will be equals to 2 into phi. That we need to prove. So what is exactly given? So now we come to the solution. What is exactly given? Given here, n is an even positive integer. Even positive integer. So what we have to prove? We have to prove that phi of 2n equals to 2 multiple phi n. Okay. So since n is even, so we can write n equals to 2 to the power k into some another integer, say m, where GCD of 2 and m is basically 1. Where GCD of 2 and m equals to 1, that is, we can say m is odd positive integer. So there is no factor as 2. Okay. So now what we can do? Now we can calculate phi of n. That means phi of 2 to the power k into m. And now since GCD of 2 and m equals to 1, that must implies we can prove GCD of 2 to the power k into m, and here we can write while k is basically natural number. That will be 1 for all m belongs to natural number. So that means we can write phi of 2 to the power k into phi m. Phi of 2 to the power k, you know, that will be 2 to the power k into 1 minus half phi n, because we know the result phi of p to the power k, that will be p to the power k into 1 by 1 minus p if p is prime and k is a natural number. So this will be 2 to the power k minus 1 into phi n. Okay. Now we will calculate again. This is, so what we get? We get phi of n equals to this. This is 1. Again, what we calculate? Phi of 2n. So what will be phi of 2n? that will be phi of 2. N is basically 2 to the power km. That means phi of 2 to the power k plus 1 into m. Again, that we can write phi of 2 to the power k plus 1 into phi m. Why? It will be phi m. Phi m. Why? Since GCD of 2 to the power k plus 1 comma m, this is basically 1. So that we can write 2 to the power k plus 1 into 1 minus half phi m. So that means it will be 2 to the power k into phi m. So what we have, we get phi of 2n. This is equals to 2 to the power k into phi m. This is 2. So therefore from 1 and 2 we have phi of 2n. This is equals to 2 phi n. Why? Since phi of 2n equals to 2 to the power k into phi m, that we can write 2 into 2 to the power k minus 1 into phi m. This is basically our phi n. Okay, so we have proved the result if n is even integer. So in that case the relation. So thus what we proved, phi of 2n equals to 2 into phi n if n is even. So this is our recall. The phi of 2n, that will be equals to phi n if n is odd, and 2 into phi n if n is even. Okay, and obviously our n is basically positive integer. Now we'll solve again some important problems. Question number 7, question number 8. This problem is also important for calculating university examination. Prove that phi of n square, this is basically n into phi n, n into phi n for some positive integer n. How to prove? So we come to the solution. Okay, so since n is a positive integer, so by fundamental theorem we can write. So we can write the positive integer in a natural number as. Okay, so first we'll take. Say here n is a positive integer since n belongs to natural number. So n may be 1 or n can greater than equals to 2. If n equals to 1, then phi of 1 square, that means phi 1, that we can write 1 into phi 1. Okay, in both cases it is basically 1. So for n equals to 1, the result is true for n equals to 1. It is very trivial case. Now if n greater than equals to 2, then by fundamental theorem of arithmetic, what we can write? n have canonical representation p1 to the power alpha 1, p2 to the power alpha 2, pk to the power alpha k, where all pi's are distinct prime, and all alpha is basically natural number for all I equals to 1 to up to k. In that case, so this you can consider case 1 and that you can consider case 2. Okay. in that case, what we can do now, what will be the phi n? Phi n square. So phi of p1 to the power 2 alpha 1, p2 to the power 2 alpha 2, pk to the power 2 alpha k. So since they are distinct primes, we can write it phi of p1 to the power 2 alpha 1, phi of p2 to the power 2 alpha 2, phi of pk to the power 2 alpha k. Since GCD of pi to the power 2 alpha I and pj to the power 2 alpha j, this is always 1 for all I not equals to j. And that we can write. So here phi of p1 to the power 2 alpha 1. So this will be p1 to the power 2 alpha 1, 1 minus 1 by p1. p2 to the power 2 alpha 2, 1 minus 1 by p2. pk to the power 2 alpha k, 1 minus 1 by pk. And that we can write p1 to the power 2 alpha 1, p2 to the power 2 alpha 2, pk to the power 2 alpha k into 1 minus 1 by p1, 1 minus 1 by p2, 1 minus 1 by pk. Okay, so that we can write here p1 to the power alpha 1. You can write this is basically n square into 1 minus 1 by p1, 1 minus 1 by p2, 1 minus 1 by pk. And since you know n equals to p1 to the power alpha 1, p2 to the power alpha 2, pk to the power alpha k. That we can write n into n 1 minus 1 by p1, 1 minus 1 by p2 dot dot 1 minus 1 by pk. And this value equals to phi n. So this is n into phi n. And since phi of n, this will be n into 1 minus 1 by p1, 1 minus 1 by p2, that 1 minus 1 by pk. So what we proved that? Therefore we proved here phi of n square equals to n phi n for every positive integer for all n belongs to natural number. Okay. Now, next problem. This will be the problem number 9. What is the problem? To prove that phi of n equals to n by 2. N by 2 if n equals to of the form 2 to the power k for some k belongs to natural number. So how to solve this kind of problem? Since n equals to 2 to the power k, so we can write phi of n, that means phi of 2 to the power k, that will be 2 to the power k into 1 minus half, because we know phi of p to the power k will be p to the power k into 1 minus 1 by p if p is prime, and hence p equals to 2 is a prime. So for that number it will hold. So that will be 2 to the power k minus 1. That we can write 2 to the power k by 2. So 2 to the power k is basically n. So n by 2, since n equals to 2 to the power. So what we get here, phi n equals to n by 2 if n equals to of the form 2 to the power k for some k belongs to natural number. So this is a simple problem. The problem may be asked for 2 marks. Okay. So now we can solve another important problem. This is problem number 10. prove that phi of 3n, this is will be 2 into phi n, if 3 does not divide n. So how to solve this problem? Since 3 does not divide n, that implies GCD of 3 and n, this is equals to 1. So now phi of 3n, that we can write phi 3 into phi n. Why? Because since GCD of 3n equals to 1, and we know phi is multiplicative function, so phi of mn equals to phi m into phi n if GCD of mn equals to 1. So that means phi of 3 means 2, so 2 into phi. Why? Because we know phi p equals to p minus 1 if p is prime. So, and if we take p equals to 3, this is also prime number. So phi of 3, that will be 3 minus 1, 2. So what we get? Phi of 3n, this is basically 2 pi n if 3 does not divide n. Okay. So now we will do some another important set theoretic function. This is basically called the tau function. So what exactly mean by the tau function? So now we come to the next important recall. The recall is about tau function. Okay, so this is represented by this. So what is the definition? First we come to the definition. The number of positive integers. The number of positive integers number of positive I am writing number of positive divisors, number of positive divisors of a positive integer n, is denoted by tau n. What is n? N is basically the natural number. So if we define tau n, so if n equals to p1 to the power alpha 1, p2 to the power alpha 2, pk to the power alpha k, and that is basically greater than, here n is greater than equals to 2, and where all pi's are distinct primes, and alpha I are natural number for all I equals to 1 to n, then what we can say, tau n, that will be the number of positive divisors of n. And this will be alpha 1 plus 1 into alpha 2 plus 1 dot alpha k plus 1. Okay. So if we define in other way, we can define in a sophisticated way the definition of tau function. So here I am saying note 1, tau of 1 equals to 1 and tau of n equals to alpha 1 plus 1, alpha 2 plus 1, alpha k plus 1 if n, this is greater than equals to 2, and n, the canonical representation of n, p1 to the power alpha 1, p2 to the power alpha 2, pk to the power alpha k, where all alpha is positive integer and PIs are distinct prime. Distinct prime. GCD of they are prime to each other. Distinct primes. Okay. So this is basically the number of positive divisors of a positive integer. Say node 2. Node 2, this you can consider node 1. Node 2, if you have asked number of positive divisors of a positive integer n, okay, that is considered as tau n, and this will be 1 if n equals to 1, and this will be alpha 1 into 1, alpha 2 plus 1, alpha n plus 1, alpha k if n is greater than equals to 2, and n equals to p1 to the power alpha 1, p2 to the power alpha 2, pk to the power alpha k, where alpha i's are natural number for all I equals to 1 to k, and pi's are distinct primes. Now we'll come to the problem. So you have asked question number 11. You have asked find the number of positive divisors of 48. So maybe this is for 1 marks question. So how to solve? So 48 greater than equals to 2. So we can think about this formula. So we have solution. Here n equals to 48. So what is the canonical representation of n? This is 2 to the power 4 into 3 to the power 1. So tau n, that means, so therefore number of positive divisors of 48, that will be tau of 48. That means tau of 2 to the power 4 into 3 to the power 1. And that will be 4 plus 1 multiple 1 plus 1. Because alpha 1 is 4, alpha 2 is 1. So that means 5 multiple 2. So that means 10. So the number of positive divisors of 48 is 10. So maybe you have asked the question, find the number of positive divisors of 900. This is for 2 marks problem. So here the solution. First we recall some basic facts. The number of positive divisors of n, that will be phi n, and that we can write alpha 1 plus 1, alpha 2 plus 1 dot dot alpha k plus 1 if n is greater than equals to 2 and n equals to p1 to the power alpha 1, pk to the power alpha k, where all pi's are distinct and alpha i's are basically natural number for all I equals to 1 to n. This is our fact. So here, what is our n? N equals to 900. That we can write 2 square into 3 square into 5 square. So by above fact, what we can write? Phi of, not phi, the number of positive divisors, the number of positive divisors of 900, that will be phi of 900. It is phi of 2 square into 3 square into 5 square. That will be 2 plus 1 into 2 plus 1, again 2 plus 1. So 3 into 3 into 3. So 3 cube, that means 27. So there are 27 positive divisors of 900. Okay. Now we come to the another important concept, another important number theoretic function. This is called the sigma function. Okay. Next we call about sigma function. Okay. So that we represent sigma. So the sum of positive divisors, if we define definition is sigma 1 equals to 1 and sigma n, that means the sum of all positive divisors, the sum of all positive divisors of the positive integer n, and this is greater than equals to 2, and that will be p1 to the power alpha 1 plus 1 minus 1 by p1 minus 1, p2 to the power alpha 2 plus 1 minus 1 by p2 minus 1, pk to the power alpha k plus 1 minus 1 by pk minus 1. What is n? Where n equals to p1 to the power alpha 1, p2 to the power alpha 2, pk to the power alpha k, where all pi's are distinct primes, and alpha is basically positive integer for all I equals to 1. So this is basically definition of sigma n, and we will say it is also a number theoretic function, and it is also the multiplicative function. Okay, so you can say here, notice sigma mn equals to sigma m into sigma n if m and n all are natural number and GCD of mn, this is equals to 1. So that means sigma function is multiplicative function. Okay, that is also another concept. Another recall the perfect number. If you will see sigma of n equals to 2n, then the positive integer n is called a perfect number. So as for example 1, you will check sigma of 6. So sigma of 6, that means sigma in 2 into 3, and by using sigma function, because 6 is greater than equals to 2, so that we can write 2 square minus 1 by 2 minus 1, 3 square minus 1 by 3 minus 1, by using the formula of the sigma function. Okay, so that will be 4 minus 1, that means 3, multiple, so 9 minus 1 by 2, so that means 3 into 4, this will be 12, and that we can write 2 into 6. So that means here we send sigma of n equals to 2n if n equals to 6. That means n equals to 6 is a perfect number. Similarly, you will check, this is the first perfect number. 28 is also a perfect number. As sigma of 28, that will be 2 into 28, that means 56. Okay, now we come to the next important problem here. Say find the sum of all positive divisors of the number 900. So this is probably our last question. So here question 11, this is question 12. Now we come to the question 13. Question 13. Sum of all positive divisors of 900. So how to solve? We have here n equals to 900. This is 2 square into 3 square into 5 square. So now the sum of all positive divisors of 900, this is basically sigma of 900, that means sigma of 2 square into 3 square into 5 square. So that will be 2 cube minus 1 by 2 minus 1, 3 cube minus 1, 2 plus 1, that means 3. So 3 minus 1, 5 to the power 2 plus 1. So 5 cube minus 1 by 5 minus 1. You will simplify it, you will see this will be 7 multiple 13 multiple 31. So this number will be 2821. Why? Since sigma of P1 to the power alpha 1, P2 to the power alpha 2, Pk to the power alpha k, that is basically P1 to the power alpha 1 plus 1, P1 minus 1, product Pk to the power alpha k plus 1 minus 1 by Pk minus 1. So therefore sum of all positive divisors of 900 is 2821. Okay, 2821. Thank you so much.